All right, let's dive right in. We're about to uncover a hidden superpower that's been lurking inside your computer this whole time. It's all about teaching your computer the secret to teamwork so it can work smarter, not just harder. Think about it for a second. Your phone, your laptop, they all have these processors with multiple cores. 2, 4, 8, maybe even more. Each one of those cores is basically its own little brain. But here's the thing. Just because they're there doesn't mean they're all chipping in on the same problem. So the real question is, how do we get them to stop doing their own thing and actually start collaborating? Well, the answer lies in this really cool concept called parallel programming. At its heart, it's just a way of writing instructions that lets us split one massive job among many different workers. Let's break down what that really means. Right now, almost every program you use runs like a single, very diligent worker. You give it a to-do list, and it just plows through it, one task at a time. It's reliable for sure, but when you're facing a huge problem, like, say, forecasting a hurricane or designing a new drug, that one worker is just way too slow. To tackle the really big stuff, we have to change our whole way of thinking, from a single worker to a whole coordinated team. So, to really get how we build that team, we need a baseline. And in the world of coding, there's no better place to start than the classic, the one and only Hello World program. Just look at this code. It's so simple, right? It's lean, it's clean, and it has exactly one job. Print the words Hello World on the screen. This is our single worker. It gets the job, does the job, done. Easy. But this is not teamwork. Okay, so what happens when we decide to turn this simple little solo greeting into a full-on group activity? What does it actually look like to ask a whole team of workers to say hello all at once? Well, brace yourself, because getting a team to work together requires a much more detailed plan. Whoa. Okay, yeah, take a second. That is a lot more complicated. We just went from a simple little 3-line note to what looks like a full symphony score. This right here is what coordination looks like in code. But I promise you, it is not as intimidating as it seems. Every single one of those lines has a job, and we're going to figure out what it is. Here's the key. You have to stop seeing this as one single program. Instead, think of it as a playbook. Every single player on our new team gets a copy of this exact same playbook, and it tells them their role, who they are, and exactly how to talk to their teammates. So let's open up this playbook and look at the core rules. There are just a handful of key ideas we need to get our heads around to understand how this whole team operates. First up, the main strategy is something called SPMD. Sounds super technical, but the idea is actually incredibly simple. It just means everyone gets the same instruction manual. Imagine you're building furniture with a few friends. You all have the same booklet, but maybe you're working on the legs while someone else tackles the tabletop. Same instructions, different pieces of the job. That's it. Okay, so next question. How does any given worker know which part of the job it's supposed to do? Well, that's where its rank comes in. Just think of it like a jersey number. When the program starts up, every single process gets its own unique number. 0, 1, 2, 3, and so on. That number is its identity. It's how it knows who it is on the team. And just like on any sports team, one of those jersey numbers is special. Process rank 0 is almost always the team captain or the coordinator. Its main job isn't to do the heavy lifting, but to dish out instructions and, in our case, gather up the results from everyone else. All the other ranks, 1, 2, 3, and up, they're the players out on the field doing the work. And finally, how does the team actually, talk to each other? They do it inside something called a communicator. When our program kicks off, a default communicator is set up that includes every single process. It's basically like putting the entire team into one big group chat so they can all coordinate. So let's walk through the play-by-play. First, MPI init is like the coach blowing the whistle to start practice. It gets all the communication channels open and sets the team up. Then every process figures out its jersey number, its rank. The players, which are ranks 1 and up, they put together their hello message and send it over to the captain, rank 0. The captain's job is to just listen for those messages and print them out as they come in. And finally, MPI finalize is the final whistle. It shuts everything down cleanly. Job done. And this just perfectly illustrates that core action. The worker over on the left uses MPI send.
It's like he's passing a baton in a relay race, and the captain on the right is ready and waiting with MPI receive to catch that baton, or in this case, the message. It's a really simple, direct handoff of information. Okay, so we've got the code, we understand the playbook. Now for the fun part. How do we actually bring this team to life and run the program? So instead of a normal compiler, we use a special one called MPIC. You can think of this command as a special translator. It takes our C source file, our playbook, and turns it into an executable program that the computer's cores can actually understand and run. And now this is where the magic really happens. We use this command mpiexec. And see that little -N4 part? That's us, acting as the coach, telling the system, hey, for this job, I want a team of 4. We could have made it 8 or 16 or whatever we need. We get to decide the size of our team right here on the fly. And there it is, the payoff. Look at that output. Process 0, our captain, says its own hello, and then it prints out the greetings it got from processes 1, 2, and 3. It actually worked. We successfully got 4 completely separate programs to cooperate as a single unified team. So when you strip away all that complicated-looking code, this is what it all boils down to. MPI, which stands for Message Passing Interface, is really just a standard rulebook for teamwork. It doesn't solve the problem for you, but what it does do is give your team of programs a common language they can all speak to solve that problem together. And that really leaves us with a pretty mind-blowing thought, doesn't it? We went through all of that just to say hello. But if we can take this same playbook, the same idea of teamwork, and apply it to much, much bigger challenges, like predicting the weather, or discovering new medicines, or running complex financial models, just imagine what we could achieve. That's the real power of parallel programming.